Okay, well, let's work on some particular questions that people had. All right, so there's a number of questions involving the interaction of a conductor moving across a magnetic field. One person said, we're talking about a straight conductor. What do you mean by, what does this mean by straight? Well, that's the simplest case. So that was the case, I didn't have it exactly straight with the green wire over the magnet, but that was a straight-ish conductor anyway, over a magnet. That was the simplest case. When I had the coil of wire acting over the magnet, that was a more complicated case. Okay, so that's all that was meant by a straight conductor. Someone else asked a very similar question in relation to figure 1030, and 1030 was about the induced current with a wire, a straight wire in front of a magnet, inside of a magnetic field, or in front of a magnet. So if I had a sensitive enough meter, when I had that straight green wire hanging over the magnet, I turned the power on, it would make it move. Okay. If I had a sensitive enough meter, I could have moved the green wire over the magnet and it would have deflected the meter. My meter, pretty darn sensitive meter, but it's not that sensitive. So it would detect, when I had the coil, remember the action between the magnet and the coil was much stronger. It really pushed the coil away, even though the coil was actually pretty heavy by comparison to that single wire. So I had a much stronger interaction between the magnet and the coil of wire as opposed to the magnet and a single wire. And so when I had a coil of wire and I passed the magnet by it, I could generate a much more electricity, much more current that way. So the straight wire example in figure 1030 is just a very simple case of the magnet and a single wire. And my meter wasn't quite sensitive enough to pick up that level of electrical generation. Lenz's law and Faraday's law. Somebody asked about Lenz's law versus Faraday's law. Lenz's law is simply the idea that the induction of electric current always acts to oppose any kind of change. This is if it wasn't that way, then you would get runaway effects in magnetism, because you would induce some current, which would generate some more magnetic field, which would generate which would induce more current, which would generate more magnetic field, which would induce more current, which would generate more magnetic field. So if you think about it, the idea that this has to oppose change makes sense, because if it encouraged change, then one change would generate the encouragement of more change, which would generate the encouragement of more change, and more change, and more change, and you get runaway effects, which we do not find in electricity. So Lenz's law just says that this effect always acts to try to dampen down or oppose whatever changes or actions are going on. Somebody asked a question about coils. Is it in a solenoid, in a coil of wire, is it only the number of coils, or is it like the size that matters and stuff? Yeah, it's the number. In fact, it's the number per unit of length is what really does it. Now, that's sort of an idealized case which gets into more, we're getting into more physics than I think would be good. If you have a very long solenoid, it's only the number per length that matters. When you get near the edges and stuff like that, you get different effects, or if it's a short solenoid, you get different effects, and maybe then the size would have some impact. But the primary driver of how a coil of wire interacts with magnetic fields and produces magnetic fields is the number of turns per length. Okay, so we got that question. Person asked about a question of brushless motors. Well, you saw, actually, let me grab the camera. Take us over here. Well, you see, that's the brushes. That's a thing that's going to wear out. Okay, that's obviously a wear point for the. Let's see if I can zoom it more. There are certain things on which the camera just never wants to focus. And I'm not going to get it so close as I would really want. Oh, there it is. That's better. So anyhow, you can see that this is a point that's going to produce wear. So that's a weak point in a motor, and So if you can have no brushes in your motor, obviously that's a nice thing.